Thank you. Okay, welcome back. Well, welcome back to me, I guess. Yeah. By the way, so I have office hours today. Is it right after class? Right after class. Yeah. And also, I have your previous homework graded, but I don't have it right here because I haven't written down the grades. So if you want to see it, you can come to my office hours, and I'll show it to you. So today, we're going to keep talking about the Bruhat order. Now, in the last class, I showed a very useful characterization of the Bruhat order, which is the subword characterization. And that says that if you have an element of the Coxeter group, and let's say that you have some reduced expression like this, then an element of the Coxeter group is less than or equal to W if and only if it can be written as a subword of this word. That's right. So when I say a subword, I just mean you pick some of the letters, not necessarily consecutively, but they have to be in the correct order from left to right, which is why I demand that I1 is less than ... less than IK. Okay? This is the most important thing to understand about the Bruhat order so far. And another thing that I proved last time is a very useful property that the Bruhat order is graded. So I think I call that the chain property, but the Bruhat order is graded by length. Another very important thing to know. And what that says is basically if you have an element of your Coxeter group of order of length 2 less than one of length 5, then you're going to be able to find something of length 2 less than something of length 3 less than something of length 4 less than your thing of length 5. Okay. So that's what I mean when I say graded. Okay. So today I want to prove a few more properties about the Bruhat order, and one of them is called the lifting property. And it says this. It says basically if you have, maybe the best way to describe it is with a drawing of the poset. So if you have some U which is less than some W in your poset, and if you can find a generator which makes U longer and W shorter. Okay? So U becomes longer when you multiply it by S, W becomes shorter when you multiply it by S. So if U and W are elements of the Coxeter group, S is a generator, and if I have all these things, U less than W, S makes U longer, and S makes W shorter, then the conclusion, you can think about it that basically these black relations imply these blue relations, that U is less than SW and SQ is less than W. So this is kind of a useful little property that we're going to use fairly often to prove things about the Bruhat order. Okay. I find it kind of hard to remember in this way, and I think the picture is a little bit more memorable. Okay. Any questions about what this is actually saying?
So we think this is lifting U to SW and U to W?
Right, so that's why it's called lifting, because you're thinking that if you have this relation from U to W, and if you have these little relations here, then you can lift from U less than W to SU less than W, and from U less than W to U less than SW. So let's go ahead and prove this. The way I'm going to prove this, and the way I'm going to prove a lot of things is through this subword characterization. So let me just pick some reduced word for SW. Okay. Now let me multiply by S on the left to get W is equal to S1 up to SQ. Now, here's a word for W, and I claim that it's reduced. Why is it reduced? Because SW has length Q. So when I multiply by S, W has length either Q plus 1 or Q minus 1. But I'm assuming that W is bigger than SW. So if this has length Q, this has to have length Q plus 1. And here's a word of length Q plus 1. So this word has to be reduced. Okay. Now, basically what I want to say is U is less than W, meaning that U is a subword of W. So I can write U as a subword of S, S1 up to SQ. Okay? That's what it means for U to be less than W. Now, I would like to prove that U is less than SW. So what I would like to do is show that U is also a subword of this word. Okay? Need U a subword of the word for SW. Okay? Well, what am I going to say? The thing is, what I want to claim is that if let's say that my word is U. I mean, U is some subword of this. Okay. Now, if it's not a subword of this one, that means that it must be using this S. That's the only thing that can stop you, right? So let's assume that I have that S, Si1, dot, 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 up to Sik. So if I had this, if I was actually using this S, then what would SU equal? Well, SU would be equal to canceling this S and getting Si1 up to Sik. But this can't be because SU is bigger than U. Okay? And this is reduced and this is shorter. So that can't be. Yeah? That can't be. And so oh yeah. So my subword equal to U could not have been using this S, and therefore it must be a subword of this one, which means U is less than SW. So U is less than or equal to SW. Okay. Any questions about that argument? Now, if you want to prove this one, you make exactly the same argument and the same thing works. So maybe to test whether you understood this argument well, you should try to do it for SU less than or equal to W. The same thing is going to work. Okay. So this is a little technical lemma that is going to help us prove things about the Bruhat order. So, for example, let's prove. Let me tell you the next thing I want to prove. The Bruhat orders that I drew so far, they all have a nice bottom element, which is the identity, and then they all kind of become round, and then they go up to the top to a unique thing. Okay. Now, I would like to prove something to this effect. In fact, when I'm going to prove it, well, I'm going to prove this, that the bottom element is always the identity, and that you always have a unique top element in the Bruhat order. Okay. That's the next thing I want to prove. And so before I prove that, let me prove a lemma. Of course, this is only going to work for the finite case. I'll say it more explicitly. But for now, let me just prove a lemma, which is that if you have two elements in your Bruhat order, then you're going to be able to find an element which is bigger than both of them. Okay. So if you take any two elements of your Coxeter group, there is some element which is bigger than both of them. Okay. So let's prove this. And the way I'm going to prove it is by induction from the top to the bottom. So from the bottom to the top, I'm sorry. So let's induct on how long these words are. Let's induct on the length of u plus the length of v. Okay. So if the length of u plus the length of v is 0, well, that means that they both have length 0. So they're both the identity. And then you can just take w to be the identity. So there's nothing to say there, really. Now let's suppose true for L of u plus L of length of u plus length of v less than k. And now let's take u and v with length of u plus length of v equal to k. Okay. Now, basically, my plan is the following. Of course, I want to reduce to a smaller case, and so what I want to do is take something that will make u shorter, and then apply my induction hypothesis. So let me take S such that when I multiply it by u, it becomes shorter. Okay. Now let me ask you something. Why can I find this S? One way of finding it is just take some reduced word for u, and then let S be the first letter of that word. Okay. Implicitly, I'm assuming that there are words in the reduced word for u. There are letters in the reduced word for u, so I'm assuming that u has length at least 1. Okay.
Federico, how do we know that u is not reduced?
Well, there's no such thing as an element being reduced. There's such a thing as a word being reduced. So what I'm saying is, let me just spell this out. So here I'm assuming that the length of u is positive, which I can assume because one of these has to be positive. So then I'm saying take some reduced word as S1 dot 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 up to sk. So that means u has length k plus 1. No, I guess I should use something other than k. And then SU is S1 up to ST. So U has length T plus 1, and SU is shorter. Okay. So I just choose a reduced word for U, and the first letter of that word is going to work as my S that I want to find here. Okay. So let me draw the picture that I have then. It looks like this. Here's U somewhere. Here's V. Now I found SU here. Okay. And now I can apply my induction hypothesis, which says that SU and V have something which is bigger than both of them. Okay. Since the length of SU plus the length of V is k minus 1, so I can find W with SU less than W, V less than W. Okay? So, what should my common bound for U and V be? Well, hopefully I can multiply W by S and make it bigger, and that will be their common bound. So let's see if that works. Okay. What I would like to somehow say is maybe SW can be put up here, and I can show that SW is a common bound. The problem with this is that I don't know which one of these two is bigger, W or SW. So let's do the two cases. So first, let's assume that the picture actually looks like that. So if the picture actually looks like that, let me draw two pictures because there's going to be two cases. So that's my first picture, and then this is going to be my second picture. So in the first case, here's case 1. The picture looks like this. Okay, and I would like to justify that both U and V are smaller than SW. Why is that? Well, it's clear that V is less than SW because you can just see it in the picture. V is less than W, W is less than SW. Okay? So V is less than SW for free. Now, why is U less than SW? Well, it's not immediately clear, but then if you look at what this picture allows us to do, this is exactly what we need. We would like to fill in this and say that U is less than SW, and we know that we can do that as long as we can fill in the zigzag between them. Okay. So I need SU is less than U, and I know that. I need W less than SW, and I know that. And now I need SU less than SW. Do I know that? I do know that because SU is less than W, which is less than SW. Okay. So this is where I'm telling you, I'm going to write exactly what I said, and we're going to get lost in the symbols, which is why I'm telling you that it's better to look at the picture. So let me say that again slowly. I want to prove that SW is bigger than U and V. So SW is bigger than V because you can just see it in the picture. It's bigger than W, which is bigger than V. So now I need SW to be bigger than U. Okay? And now I look here and I see that if I want to prove something like this, then all I need is to prove a zigzag like this, and then the blue thing will follow. So to prove this blue relation, I'm going to prove this zigzag like this, from U to SU to SW to W. In words, SU is less than U, you can see it. W is less than SW, you can see it. And SU is less than SW by transitivity. Now let me just write all of this out. So to prove to prove this, I say that SU is less than U. I say that W is less than SW. And I say that SU is less than W, which is less than SW. Okay. So these three relations, let me put them in red here. I proved this one, I proved this one, and I proved this one. And that's exactly where I can use my lifting property to say that these three red relations imply this blue relation and then this other one, which I don't need in this case. Okay. But these three relations imply that U is less than or equal to SW by lifting. Okay. Now, when exactly can you use this lifting property? Let's look at this more carefully. You can basically use it when you have a zigzag, like as any zigzag in the poset, such that here you're multiplying by S, and here you're multiplying by S, to go from U to SU, and from SW to W. Whenever you see a zigzag in the poset, where you're multiplying by S in parallel like this, you can use the lifting property. And that's exactly what I have here. Here I'm multiplying by S, here I'm multiplying by S, and I have the zigzag that I need. Okay. So that does it. Okay. Any questions about it? Let's do it in this case. I think I need a better picture. So this is case 1, right? Now, case 2 is that W is bigger than SW. Okay? So in my poset, that's going to look like this. Okay? So what can I say now? Again, let's try to stay away from the symbols and just look at this picture right here. Before I do that again, let me just make sure that we understand all the hypotheses that are implicit in this picture. So first, what I did was assume that SU and V had a common upper bound, which is W. W is bigger than both of them. Okay? SU was built so that it was smaller than U. And now, according to case 2, W is bigger than SW. Okay? So this picture I can see in my poset. Now, you see where the lifting property takes place. You see the zigzag, right? Here's the zigzag, where here I'm multiplying by U, and here I'm multiplying by U, by S, I'm sorry.
How do we know that W is not the same size as V? This isn't, it could be, we're still going to have to value.
Because, well, it could be equal to V, but it can't be smaller. So I assume that W is greater than or equal to V, which is why I'm drawing it like this. But you see then, the only thing that I can do here is complete the zigzag. Here I have the zigzag, so I can lift this to this and to this. Okay. But what am I trying to prove here? I'm trying to prove that U and V have a common upper bound. And I found it. It's W. So by lifting property, U is less than or equal to W. And I already knew that V is less than or equal to W as well, which means that I found a common upper bound for U and V. In case 1, the common upper bound was SW. Yeah, they're both less than SW. In case 2, the common upper bound was W. But in any case, they have an upper bound. They have a common upper bound. Okay. So that's my lemma. And given that lemma, I have an immediate corollary which says that in a finite Coxeter group, there's a unique maximum element, which I'm going to call W naught. Okay. I don't know about you, but it took me about 2 years to understand what people were saying when they were saying W naught. So they're saying W naught. Okay. So this is what this is. Okay. People don't like to call it W0, they call it W naught. So if my group is finite, then there's a unique top element that is bigger than everything else in the poset. Why is that? Well, basically because you just look at the poset, right? And you look for the top things. And if there are several top things, there really can't be, because if you have two of them, then there's something bigger than them. Okay? So if I had two maximal elements, U and V, then I have two elements and they have an upper bound. Then I would have a W which is bigger than both of them, and that contradicts that they're maximal. Okay?
I'm not seeing why. Couldn't the upper bound be one of those elements?
Because it could be one of them, but then, for example, if the upper bound was U, then that would say that U is bigger than V. And that would say that V is not maximal.
It'd be U bigger or equal to V, right?
But they can't be equal because there's two of them. Yeah, so that's why. So if I have two different elements, they can't both be maximal because they have a common upper bound. And that means that I can only have one maximal element. And if that's the only maximal element, then it has to be bigger than everything in the poset. Okay.
So we're really using this lemma.
We're using this lemma to obtain this. So it's a corollary to that lemma. Okay. So let's try to make this concrete in the example that we know very well. The symmetric group. So according to this, the symmetric group Sn is finite, and therefore it has to have a unique maximum element. So what is the unique maximum element of the symmetric group? Well, there's one thing we should remember, which is that the Bruhat order is graded by length. Okay, and so by saying that I have a unique maximum element, I know that that unique maximum element is the only thing that has its length, and everything else is shorter than it. Okay, so what is the word of maximum? I mean, what is the permutation of maximum length in Sn? Well, let's remember what the length of W is. The length of W is the number of pairs which are out of order.
Would be a permutation looking backwards and then minus one.
Exactly. So it would be the permutation where everything is out of order. Every pair is out of order. What's the length? Well, basically it's the number of pairs, right? And choose two. I should also tell you that sometimes people call this the long word. So sometimes you'll see it. This W naught is also being called the long word. So if you catch me saying the long word, what I mean is W naught. Okay. And I should say that I'll try not to say the long word because I don't like this name. And the reason is that W naught is not a word. W naught is an element. It's the top element, but it's not a word. I mean, there's many different words for it in the generators. Yeah. For example, this is the longest element, and I can obtain it in many different ways as a product of the transpositions Si. Okay. But if you ever see people saying the long word, that's what they mean. Okay.
Wouldn't that be the longest word?
Yeah. It should be the longest element. Actually some people, but if I say the longest element, then you know what I mean because that makes sense. So I should only tell you when something doesn't make sense. I should tell you what they mean. So when they say the long word, they don't make any sense, but they mean W naught. Okay. Okay. Now let me prove a nice converse actually to this, which is that if I have a unique maximum element, then my group is finite. It's not obvious, actually. You should think about why it's not obvious, because I could have infinitely many generators that maybe all collapse and make a finite and make it finite height. So converse. If there is something like this, and I'm going to assume something weaker. I'm going to assume that every generator makes it shorter. So I'm only assuming that W naught is bigger than the things obtained by multiplying on the left by a generator. I claim that this is enough to say W naught is the top element and W is finite. Then W0 is bigger than W for all W in the group, and the group is finite. Proof. So let me just induct on I don't know. I think I should just leave this to you as an exercise. I mean, it's
Say something about the length of W
No,
naught?
no. This is all I have to assume. So I'm only assuming that W naught becomes smaller when I multiply by a generator. Okay? And I claim that that's enough to guarantee that W naught is the top thing and the group is finite. Okay. So this is an induction on W. And I think maybe I'll just make this an exercise for you to practice with these things that we're proving. So let's make this one of the homework problems. Well, you'll see how it goes. So now once I have proved that W naught is bigger than everything in the poset, how can I guarantee that the poset is finite? So here's W naught, and everything is smaller than it in the poset. Okay, but it could be that, I don't know, maybe floor 4 has infinitely many elements, conceivably. So why is it that we can't have that? Well, there's a simple reason for that, which is that if I pick a reduced word for W naught, so let's say it's S1 up to SQ reduced, then all of these guys are subwords of this. So there can only be at most 2 to the q of them. So all subwords. So there's at most 2 to the q of them. And that proves that the poset is finite. Okay. Which is good. Says that these posets are not as strange as they might be. Okay, any questions about this so far? Okay. So now what I would like to do is prove some properties of this W naught. So for example, here's a property. W naught squared is the identity. Okay. Now this should seem very mysterious to you. I find it very mysterious initially. For example, this says if you take the reverse permutation and you square it, you get the identity. In that case, it's not hard. Now the proof is not hard. It's kind of nice actually. What's the length of the inverse of W naught? Well, we know that an element and its inverse have the same length. Okay, but this is supposed to be the only guy of its length. And that means that this has to be the same guy. It's very, very slick. I did nothing and I proved something. Yeah. But yeah, so then, and this is the maximum length. And that means that these two guys have to be the same element. And there you go. That's the proof. Now, the next thing I would like to prove is that the length of, when you multiply an element by the longest element, then the length that you get is this. Okay, so what this is saying is, you go from the bottom floor to the top floor. Here's the identity, here's W naught. If you take something in the floor K and you multiply it by W naught, then all of a sudden it goes to the floor N minus K. So, proof. Let's prove both inequalities. Okay, so how do we prove this inequality? By proving that the length of W plus the length of W naught is greater than or equal to the length of W naught. And this is one of your homework problems, basically. This is the triangle inequality for the metric. For the metric of the homework. Okay. So you proved that already. And this we just proved by induction. You prove it by induction from the top. So first you prove it for W naught. Okay. And then you prove that if it's true for W, then it's true for SW, when SW is shorter. Okay. I think I'm trying to rush too much, so maybe let's just prove this carefully, and then I'll continue next time what I want to say. So what is this statement saying for W naught? For W naught, this is saying that the length of W naught is equal to the length of W naught minus the length of W naught. Okay? But now that we know that this is the identity, I'm saying 0 is equal to 0. Okay. Now, suppose it's true for W, and now let's take some SW, which is less than W. So, what am I saying? I'm saying it's true for W, which means that the length of W naught is less than or equal to the length of W naught minus the length of W. Okay. Now I would like to prove the analogous inequality, where instead of W, I have SW. Now, so how do I do this? Well, I say, first of all, what is the length of W? I can write it as, how big can this be? Well, I'm taking something and multiplying it by S. So by doing that, I can at most increase the length by 1. Now this is less than or equal to the length of W naught minus the length of W plus 1. And what is this? The length of W minus 1 is the length of SW. Okay. So I'm done. Okay. Now what I'll prove to you next time is that not only is it true that multiplying by W naught sends you from floor K to floor N minus K, but what it does is that it flips the poset in a sense. So I'll prove that next time. Okay. But that says that W naught is a very nice element of the group. All right. Is there any questions in the meantime before I erase this stuff? Wait, no, the length, no, that cannot be infinite, because, you know, by definition, group elements
W is a permutation.
are
Back when we
finite
talked about
words.
Yeah. Okay. So it just means whatever the image of A is.
So each element has to have a finite
For
number.
all A, let's see.
So the only way we can at least this could be infinite is,
Yeah. So what you end up is they're saying you have an A, B, C.
no, you still have to have,
Ascending order. You don't end up switching.
Right.
The intervals are
finite
finite.
minus 1.
So,
The way these things can be
but
infinite
I got
is
the range
kind of
basically.
practical.
doesn't though.
What that means is you have a
Once it looks like
transposition
this,
that's non-adjacent.
like this.
We know that all our
It never
non-adjacent
closes up.
transpositions
Are reflections.
are reflections. All reflections are palindromic. So they all have to have something like this in them.
I mean,
This is just when we don't have.
when you don't have a top element.
Okay.
And what this is saying is if you do have a top
Oh, no,
element,
yes, right. Okay.
So then it closes up.
If you left out the C,
What are we
okay.
saying about our generators?
But with that C in there, you have to have
Yeah.
a non.
so listen, so you assume that you have a top element.
Wiring diagram.
No, what if we don't?
Right. It means
Yeah,
that you're
so
leaving
all
something
this I
in
agree with.
between, in the right order, but changing the
So you're worried about what happens if we don't have a top element?
Right.
Yeah, it seems to make
So you didn't say in a Coxeter group there's unique maximal element. You said in a finite Coxeter. So in an infinite Coxeter group,
You said,
what if this blows up?
we're talking about the range
And actually,
there, or
I mean,
what?
there's an example in the
Oh,
homework.
no, I'm
so
talking about the Bruhat order.
follow one of them. right?
Contains this.
They are infinitely many symmetries.
I'm not sure what the left
Then you
one
add
is
an S,
in this case.
an S, you know, like the same number
So
was
that means
So
that there's
last
a top
time?
element.
why can that not be a reduced word then? I think it
I
has to do with
think that it's actually just
And
talking
if you got the post-it, actually, it looks like,
one element that
I think the way it looks like
from
is,
what I researched on the internet and what I understood of it when I just played with it. That's meant that the orders are different, so that if the image, if you have 1, 2, 3,
yeah, I mean,
when you're in like, if the image of 1 goes to 4, and the image of 3 goes to 2, but the image of 2 only goes to 3, so it's still in between them if the other 2 are switched. So 1 is now greater than what the image. That's why
Okay, so now, I mean, that's what you're saying for that one. I think that one
Yeah,
is
I think that
reasonable.
it's comparable.
I could try to recreate half the truth. I don't know if it's half.
Right,
So it's saying we don't contain any transpositions.
right. But I think the first way is really easy if you use the translation. Or the contrapositive.
So let W be a permutation.
So one of your elements.
Then this says that W contains no transpositions. Oh wait.
I mean, you can certainly see the lattice if you write down like all of it. So it
Well, this is a
you
particular
build
thing.
these triangles.
Any reduced combination contains something.
I mean,
Yeah.
you guys do this problem?
So that means that like no reduced combination W contains a anything looks like a transposition.
It's not because that pretty much eliminates all your non-adjacent. Because we know where all of those are. They're in the
And then when we say that, we say, well, okay, assume this is true, and then say, well, can this be the case?
It looks like,
So we're gonna see.
Or let A, B, and C, and
depending on
let's
how
put
we're growing.
and then can this be the case? No, because
I want to say that it looks like.
it's almost the same argument.
Yeah, it's not really that hard.
No, a lot of it's just it's the notation, or a lot of it's that I really get the book.
Oh, I have the book right
This sounds reasonable to me. I'm not very convinced of the truth, but I think it's true. You heard of buildings?
Buildings?
Well, mathematical buildings.
I think I've seen the word somewhere.
So this is a building. Yeah. That's why I think that it might be this because it's a very natural mathematical object.
And did you get my email about that paper by
Oh yeah,
Bolton or something? Something.
Yeah, I haven't read it back. And it sounds good. I haven't looked at it carefully, but so let me have a closer look. And actually, my thesis is very close to that, and I think you should have a look at that also. It seems that what this guy is doing in his article is
invitation.
No, not really. I mean, will you be around to talk about it later? I was
Oh, you're gonna go upstairs?
Yeah, I was hoping.
Yeah, I'll be here. Come on, Eric.
You'll be here.
I will be upstairs in the conference room until, from now until 6:30 minus 3.
Okay. Sounds good.
Set.
Thank you.
Whenever the and bad.
Huh?
And bad.
Ampad?
The ampad.
Ampad, yeah.
And the app, but it's actually kind of a cool way to write up your homework.
Are you doing that?
Yeah,
This time?
Hell yeah.
Hell yeah.
I can't go to Kinko's. Didn't trust those people.
It's from 4:30.